Okay, so now it's going to be a very light session on what natural language processing is, what ideas are behind it, and so on. And I hope you can appreciate like why I'm so excited to work in this and so on. So first, before we get into language, I want to talk a bit about intelligence and artificial intelligence. So what are the characteristics that make programs qualify to be called artificial intelligence? We have a lot of programs, like, from washing machine to mobile phones to like space programs. Everyone claims they are using AI in their method. So what is it? What differentiates AI from other programs? So many scientists, computer scientists, psychologists have come up with uh, certain key core factors that measure intelligence. Okay, and these are language is one of them, because it is still a wonder how we learn languages, and uh, especially Indians learn multiple languages depending on what your mother tongue is, what place you are in. We pick up languages also quite fast because we're such a diverse nation. And the next one is representation, which was similar to the discussion we had before on 2021, whether to use Roman numerals or not. Powerful representations are a cornerstone of intelligence. Um, and there is a saying I like a lot, which is, what is a man that he may know a number, and what is a number he may know a man, which basically means, how does a child understand that the number 7 represents 7 entities? It's just a set of lines, but we are so intelligent that when we are taught addition or subtraction when we are 5, 6, 7, we understand that it means number, it can be added, it can be subtracted, and that we don't know how our brain is representing such complex concepts. Not only are we representing it, we are also reasoning with them. That is what I meant by like adding or subtracting and so on. And these two are perception and action, which means we can perceive the input. Here, perception is not understanding, it's more like receiving input. And action is how you act on it. Now, in AI, each of these becomes a field. So, language is called natural language processing. Representation is knowledge representation. We have knowledge reasoning. These both are usually clubbed together because the reasoning depends on the representation. And the perception and action comes in the field of robotics, your self-driving cars, and so on and so forth. We also have things like representation learning and so on. So these are the factors that determine intelligence. It's not like, for me, a very naive understanding of intelligence was just collection of knowledge about various things, and that's what we've been taught from childhood. But intelligence is far more complex than that. It's how you process language, how you process ideas and concepts and things like that. Of course, it improves with knowledge, but it's also the idea that our brain can do that, which is very fascinating, especially when you code it for computers, because we don't know. We, in the sense, even like brain surgeons and things like that, people like that have no idea to what extent we are representing information, but we have a fair um, high level idea, which is what is helping us do this. Now in AI, we have machine learning, automated reasoning, knowledge representation, problem solving, perceiving and acting. Now perceiving and acting has natural language processing, computer vision, and robotics. Deep learning is very successful at this. There is a saying, I think it was Andrew Ng who came up with this, which basically said any task that a human takes a fraction of a second. For example, you see your best friend. You might see that best friend in different clothes, different hairstyles, but you will immediately recognize it is the same person, which was a challenge for computer vision at some point in time. But this is something you don't even think. It comes so naturally to you. Similarly, you listen and understand words very fast. So these are things that we perceive within a fraction of a second. And these are the things deep learning models excel at. And that is going to be the focus of our course. And all the others are very different ways of approaching these problems. I'm sure many of you would have heard the Turing test. Can someone just summarize it for me? Have you come across the Turing test?
Yes, ma'am. So
Yeah.
like for any, like if I'm a human and like if
Mm-hmm.
I observe a set of actions done by either a computer or a person, I should
Mm-hmm.
not be able to differentiate if it is being done by a computer system or a human being.
Exactly. Fair enough. So thanks for that. The idea is that this Turing test was also primarily designed on language. So what the human is going to get is basically a set of language statements, and you're going to see whether it came from a computer or a human. And this particular branch of reasoning is called mimicking human behavior. Because you see, humans don't behave in rational, perfect ways. For example, one of the easy ways of figuring out if it was a computer or a human was to ask a random number, like what is 9 to the power of 18? A computer would actually calculate that and tell you, but a human would be like, what are you asking? So it's not a perfectly random answer, but it is a human answer. So the idea of a Turing test was to force algorithms to give a human-like or friendly, approachable material. Now, the Turing test was passed a few years back because it convinced 33% of the audience. It's not like it convinced everyone. From 100%, it convinced 33%, but they won the prize basically a few years back. And that is quite interesting how far we have come. It seems like a simple NLP problem, but it involves all the aspects of intelligence I had touched upon. You'll have reasoning, you'll have representation, you'll have language, and except of course perception and action you don't have because it's not a robotic session. But the other three you do have that. It's more like on the software side. Now we come to language. What is language? What are we doing? Why is this interesting? And why is it such a relevant real world problem? Now, first, let me just touch on what is natural language and what is a machine language. And we know machine language is binary or your assembly or your programming, and natural language is what human beings speak: English, Tamil, Hindi, Bengali, whatever it is. So, the problem is natural languages have evolved over time. Though we have grammar, we know there are a lot of exceptions. When I was learning Hindi, I was told that words that end in "a" are feminine, and the exception was something as basic as ladka, which is like a very commonly used word. So what that means is languages evolve over time. There is no set grammatical rule, and we all know English is a crazy language. You can have so many variations that you cannot pinpoint a certain rule. We'll be seeing the various challenges in the coming slides, but I think you can appreciate the complexity of the task. So what is natural language processing? We use computer science, we use theory from linguists, and we use AI and machine learning to do a set of tasks. How we do it, what is the outcome is what gives the richness to the field. We have two major strands, which is understanding and generation. By understanding, I mean given a piece of text, I should be able to extract information from it. So given, say, given a research paper, I should be able to generate the summary of it. In generation, for example, I have to generate a natural language text based on some numbers, like a weather report. I have censored information and I'll generate a report that sounds logical or sounds human or sounds like something you would read in a newspaper. So that is natural language understanding and generation. Um, from experience, I can say that understanding is far harder than generation, because generation you have some control over what is happening. But in understanding, literally anything in the world you can type. And I'll show some of the examples also. But that does not mean generation is very easy, because if I have a lot of sensor values and I'm just going to output that as sentences, it's going to be very monotonous and repetitive. How we design it makes a very interesting task. So we'll touch upon the challenges. We have complexity, as I've been mentioning quite a few times now, the context, uh, disambiguation, co-reference resolution, syntax, semantics, common sense reasoning. These are some of the reasons I have been able to recollect, but there are like many, many more. So we come to complexity. I love this part of the discussion because it makes you really think about language deeply. So the first thing is, time flies like an arrow. If you ask the computer to find out what is the part of speech of time, you will be surprised that many times we get very different answers. We know that it is a noun here, and you're saying time is flying like an arrow, so it's going fast. But sometimes it gets classified as adjectives. Why? Because we have sentences like fruit flies. There it's an adjective. Now there's another complication when you're trying to understand that fruit flies are a type of flies. Though it is adjective, it has no correlation with the word fruit at all. So these are the kind of funny things with language which are quite detrimental to your program actually. Then the usual noun that we expect. One more surprising interpretation is using it as a verb. Like, time the flies as fast as an arrow, something like that. And each of these words have various meanings. Like time flies like an arrow, in the sense there are fruit flies which like arrow like a banana, something like that. So time flies like an arrow is a very commonly used example to show how complex language is. And then we have the classic disambiguation problem. What if you have words that mean different things, like homonyms or synonyms, which are different words with similar meaning? How do we overcome all of this? How do we model them? So basically, Bank of Ganga is very similar to Bank of Baroda, because they're both could be taken as places. But we know that this is basically a river bank and this is a financial bank. How do we disambiguate it? If we have to look at the context, how long do we look at it? So if I say in this bank something, 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 in a text, every time I see bank, I'm not going to write, oh, this is Bank of Baroda. In the Bank of Baroda, I deposited some money. I walked to the Bank of Baroda today. No, I might as well write, I walked to the bank and then write one huge Purana. And in the end, I will be writing, it is Bank of Baroda. But because I was talking about walking and things like that, it is equally applicable to a river bank. So how long should I look for a context? Should I look for 5 words? Should I look for the entire paragraph? These are all meta things you need to keep track of for your data set, for your domain. And that is quite hard. And it comes only with like experience, and even then you might not have a very good model. And right now, that's what is interesting. There's so much more to be done in NLP. Though a lot has been done, there's still so much more to actually understand how language works. The next one is very interesting. It's co-reference resolution. What do I mean by co-reference? In a sentence, I have a lot of things referring to other things. To give an example, I threw a ball and it hit the window and broke it. You and I know that broke it refers to the window. But the machine can say that it is window, it is ball, it is me. If it is slightly intelligent, it will at least rule out me, but it will still be confused between the ball and the window. Now, this task is coreference resolution. It is applied to pronouns mostly, but it is also applied to nouns. If I have a long sentence and I have nouns which are similar but refer to the same thing, then it is also called coreference resolution. This is again a very hard problem because it involves not only the grammatical structure or whatever is given within the text. For example, in this, even though there is ambiguity, uh, with sufficient amount of contextual information, I can disambiguate. This, on the other hand, apart from the text, I need to have some knowledge that a window is breakable and a ball is not. And also that is usually the case. There might be some person who wrote it for the ball also, but I know that it is very less probability. And this information is not going to be there in your text at all. That look, okay, computer, window is breakable, so this is going to be your coreference. And the way we need coreference is for dialogues or question answering and things like that. And we've only seen it get more and more complex. The next is, so far we've been looking at words, their grammar, what do they mean. This is taken from Noam Chomsky's work, which is basically he was very skeptical of machine learning and deep learning methods for language modeling. And he said, look, your data might generate a sentence like this, which is colorless green ideas sleep furiously. Now, it is a perfectly grammatical sentence. There are two adjectives. We know we can put that because we write things like a big red ball. So big and red are two adjectives. Like that, we have colorless green. But colorless and green cannot go together at all. They are opposites. Not only are they opposites, they come with the word ideas. What is a colorless idea? You've heard distilled water is colorless, odorless, and all. What is a colorless idea? It makes no sense. On top of that, you have things like sleep furiously. So the thing is, grammatically, this is perfectly fine. You have a verb, you have an adverb, you have. So basically, when you work in NLP, you become very well versed with whatever you learned in high school or middle school English, which is like, what are the parts of speech, what is the interjection, what is the difference between a declarative and an imperative sentence, and so on. And in spite of having that, it's quite hard to model all of this. So there is a very famous debate between Noam Chomsky and Peter Norvig. I will be sharing that in the material, which is basically both of them are arguing that Chomsky says you need a grammar to specify how a language works. Norvig says no baby in this world has this model of a grammar and learns language. A baby learns language from examples, from hearing people. But Chomsky's idea is that human beings innately have this grammar. It is birth given, and that's what is coded in our prefrontal cortex, and that is how we are understanding language, because we have this natural gift to understand grammar. And both of them argue very interestingly how language should be modeled. And it gives us some food for thought. Do we need to say that, okay, we have a perfect grammar, or we learn from examples. Now, this is anyway following perfection. So even if you have grammar, it also requires semantics. So this is how Chomsky and Norvig. So Peter Norvig, you might have used the textbook AI, Stuart Russell and Peter Norvig. Their textbook is the classic basic textbook. And both of them have opposing views, but their ideas contribute to how we process language. Now, language processing is not purely data driven, nor is it purely rule driven, as Chomsky would say. We will see how the interplay of both is required. Next is common sense. I already hinted this in the co-reference resolution part, where we needed the fact that it referred to the window. This is another example. I went to the park and shot a few pictures. Many algorithms reported shot as shooting with a rifle, because there were many sentences like, I went to the park and shot a bird. So differentiating them is quite hard. Now you can see that all of these problems are sort of interrelated. I can even say this is disambiguation and so on. Usually ambiguity and common sense go hand in hand, so to say. So to summarize, the issues are interrelated. And language is organic. The rules are only indicative. There is no hard and fast rule for language. And language constantly evolves. Today we have a word Google that everybody uses as part of their language. It's no longer a proper noun. So over time also language is evolving. And language is highly expressive. You have, especially it's very interesting. I worked in language processing for Tamil, where the sentence order itself does not matter. I can say like aval pogiral or pogiral aval, both of them are quite are grammatically fine. So it's quite hard to model language, and I would say Tamil is one of the toughest languages to model for a computer. So I already touched upon understanding and generation. I just wanted to give a few examples of both. So all your digital personal assistants, Siri, Alexa, Cortana, all of them have some amount of natural language understanding. Though at this stage, I suppose most of them are just if-else rule sort of thing. But nevertheless, it is some amount of understanding. We have the autocomplete in our phones. That's also a language problem. Spell checking, machine translation, sentiment analysis, question answering, chatbots, automatic summarization. All of these are in the generation. Today in industry, everyone has a chatbot. So much that you have to ask, is this a bot or a person you're talking to, right? And that is due to deep learning that it became so ubiquitous. Then you have automatic summarization, weather report generation, and question answering. Question answering is unique in the sense it involves both understanding and generation. So we have three major ways of approaching natural language processing. And in this course, we will be focusing on the deep learning part. But I want you to appreciate where we came in terms of language. And in the next class, we will be looking at this evolution a bit more in detail. But I wanted to give an introduction here. So first, we had the symbolic AI methods, then the statistical machine learning methods, and then the deep learning methods. So first, the symbolic AI methods. What do I mean by symbolic AI? Basically, the period in time where we dealt with assigning symbols to language and then processing them. So this is Eliza. It's a program. It's a chatbot, basically one of the earliest chatbots. I think it came in the 60s or something. And it goes like this. Hello, I am Eliza. Hello, Eliza. Yes, ask me some questions. How are you? Some things like that. Now, the thing is, how Eliza works is very simple. It has a very, very simple grammar, few phrases, and the trick with Eliza, which made it seem very convincing, was that whatever you answer, it will just um, transform it a little bit using some grammatical rules and give you some sentences. And also, the author realized people ask Eliza very standard questions. And so there were already a set of templates. And then, depending on your answer and those templates, very simple modifications. You will not believe. See, when you read this, it looks so convincing. Do you have something to talk with me? Are you beautiful? Usually, people say, I am beautiful. Now, this looks like it's very convincing, but in the program, there is just a code which says wherever there is RU, convert it to IN, and there are um, a set of introductory phases or post phases, things like that. But it was so convincing that the person who invented this, his secretary was talking to Eliza as if she was a therapist. And that's because humans have such complex ideas and we can extrapolate something to something that doesn't, exist. So that was the success of Symbolic AI. This is, of course, a very simple program, but Symbolic AI also had a lot of complex programs, a lot of interesting ideas that were put into the machine. So mostly they would deal with modeling language to understand more and more complex things. But the drawback was there was no way to compare these algorithms. One algorithm would say, I took care of these set of sentences. Another algorithm will say, these set of sentences. The machine learning approach brought in data sets and a way of unifying all these algorithms. So I can compare that, okay, this is better than this in this aspect, and so on. So in the machine learning approach, it's what we do, we convert the text, a human converts the text into a vector, and then it's purely mathematical. There is no rules or anything like that. It's just we have a training data with input vectors and output values. We use ML algorithms to predict. For example, if you take sentiment analysis, we have a vector indicating whether the words such as good or bad are present. Maybe the vector will be large. One of the features is this, and the sentiment is 0 if it is bad or 1 it's good. And classification algorithms, now they have a mathematical representation, a vector like we saw xi or something like that, and the output. So what do I mean by this? In Symbolic AI, if I have to represent the concept apple, I would give, the human would develop a hierarchical representation where you say, okay, there is a structure, there is a kind, which is a flute, and then its color can be red or green, and its size is usually the size of a fist, and so on and so forth. In ML or in neural networks, mostly we say it's a connectionist apple in the sense, I have a set of nodes, and these have different weights, and finally I get a classification. Now, the drawback of this is I don't have any meaning to these numbers. In a symbolic case, I'm very sure that this is what an apple is. It has so many features. It's much richer. But it is very hard to apply this to language and find such a structure and get the classification required. So that is why these methods sort of died down, because it became more an exercise to flaunt the developer's intelligence than to actually solve real world problems. However, that does not mean doesn't have its merits. In fact, now we are looking at merging the two, because you can see there's a lot of information in this. So if somebody has already taken the pains to model a domain, why not use it? We have not been able to harness it, but maybe there is a way to combine it. That is what we are currently researching. Now, next is, how did we learn languages? Because that gives us a clue what we can do. I already touched upon this. So this is Goddess Walk in Rigveda, who's an embodiment of speech and language, and she evolved to like goddess Saraswati later on. And this is the Tower of Babel's Christian story where you say that all the human beings in the world were trying to build a tower to reach heaven, but God gave languages, and all of them started talking in different languages and could not communicate, and the construction was stopped. So, what these two stories indicate is that people have been fascinated where languages came from and how did we learn language. And this brings us back to the Peter Norvig debate. Is it, do we have an encoded grammar, or are we learning just by hearing? Are we developing a model just by hearing examples? And as far as language is concerned, it seems like we are learning from examples. But the difference between how deep learning methods learn languages, the fundamental difference between how deep learning methods learn languages and how we learn languages is that we don't need so many examples. We need very few examples, and we don't forget also. So if a deep learning model has learned the difference between um, say the words cat and dog, and then you train it for something like the words apple and orange, there is no memory of the cat and dog at all. It is completely removed. So I already spoke about knowledge that we have lost from symbolic AI in deep learning. We also don't have the concept of memory in deep learning. These two are some of the major, stumbling blocks in deep learning for NLP. So to sum up, in AI, the work is really tedious. It involves a lot of troubleshooting and problem solving. In machine learning, it's a bit better. I am teaching the program to learn based on a vectorial representation I am giving. In deep learning, I have become extremely lazy. I've just given the text as it is and asked it to learn, basically. So as you go from AI to deep learning, of course, this is not like they are separate things. Machine learning is a part of AI and deep learning is a part of machine learning. But as you go on from here, you see that human involvement reduces and complexity of the algorithm increases. And one more thing is, in AI, whenever you get an answer, you can be 100% sure it is correct. But the problem is your rules will rarely trigger and you will not get the answer. That is why these methods became popular. Even though these methods have errors and it is not deterministic like the AI methods, they became popular because they became applicable and generalizable, which this lacked, especially for language. So we'll look at the language processing tasks in a bit more detail. So we have 6 levels of language processing. First is the speech sound, which is even before the words. We are seeing the phonetics and the phonology. What are the sounds? What does CH represent? Is it chips or is it Christmas? What is the connection between spelling and sounds? That is the first level. The second one is the word and their forms. What is the morphology? We'll see examples of that. So this is at the word level. Then we have the structure of the sentence, which is the grammatic or the syntax level. Then we have the meaning of the sentence, which is the semantic level. Then we have the meaning in context and purpose, that's called a pragmatic. And discourse is the last level, where you take the entire document. So context is a small window of the word, and in discourse, it's an entire piece of text. So this is the gradation, and this is one way of classifying. There are other ways. So the first way is sound, like I said, whether CH is ch or k or what it is, and things like that. The second one is the morphology or the structure of the words. Uh, what is the plural of dog? It's dogs. Plural of ladies is ladies. But the structure of the suffix is different. Structure of the verb, past tense, dogged, and so on. Should we store all of them in a dictionary? because we have things like in some English, fish and fish is plural, in some fish and fishes are plural. They even vary based on the location. And we have a general set of rules, but we also have a lot of exceptions. Uh, More often than not, the exceptions we are forced to store for a simple solution. The next one is the syntax. Ram goes to the market, goes round to the market is wrong. But in Tamil, both of these would be correct. That is what I mentioned. Next is, so this was the grammatical part. Next is the semantic part. So in semantics, we extract information from the text. We are saying agent is Ram, source we don't know, where did he start from, but we know the destination is market. So this is the the fourth level. The fifth is context. Is that water? Will the interpretation will differ largely if it is in a chemistry lab or on a dining table. The last one is the discourse level. And this, I already mentioned, it comes under co-reference association. Man went near the dog, it bit him. So it refers to the dog, not the man, and so on. And even this, the computer might not get so confused because dog is it and him is man. But definitely, dog went near the cat, it's very difficult. Forget computers. Dog went near the cat, it bit it. It's impossible for humans also. How will you say that whether it's cat or dog? You might have a logic that possibly the dog is larger, but we don't know. It could be a tiny dog and the cat bit it. This is interesting because this is a disambiguation even humans can't do. So that is the complexity of language. But usually these cases are quite rare. So now we come to the commonly used NLP tasks. The first one is common sense reasoning. We already discussed quite a bit about that in a lot of examples. The next one is constituency parsing. In constituency parsing, what we do is basically we build a tree. We say that, okay, there's a sentence. It has at the first level noun phrase and a verb phrase. The noun phrase has noun, determiner like a and so on. So there's a tree. It starts from the sentence and there's a tree. This is constituency parsing. Co-reference resolution we already talked about. Next is data to text generation, which is like weather report and lot of sensor information. We need reports. One of my lab mates worked on this code project where you take a lot of inputs from the industry settings and generate a report. The report was not very fancy or something, but it really helped people take policy level decisions. The next one is dependency parsing. Constituency parsing and dependency parsing are similar, but the domain is different. In constituency parsing, we have this, okay, it's based on the structure. So we have a sentence, verb phrase, noun phrase, and so on. In dependency parsing, what we have is it's a higher level. So we have things like subject, entity. So you recognize things, whether it is an organization, whether it is a person, and so on. It even has these days dependency parsers even have date organization, what date it is, what time it is, and so on. So that is very interesting. And it's quite hard to do, but thanks to deep learning models, it has become almost a solved problem now. Next, we have dialogue, as I mentioned in chatbots. We have domain adaptation, where we have related domains and we transfer the knowledge. For example, if I have a lot of Amazon reviews on multiple products, I I share knowledge between many of the reviews and come up with a language model for reviews. Next, we have entity linking, which is basically entity recognition and disambiguation. For example, I can have SSN College of Engineering and SSN. Both SSN College of Engineering and SSN would be recognized as two entities. But the fact that both of them refer to the same is what is done in entity linking. Then we have the grammatical error correction. This we have seen in words since our childhood and things like that. And initially it did not use any AI, but now it is using quite a bit. Then we have information extraction. This is a very large field. There are so many applications of information extraction, and it's a very simplistic way of telling, because we have shallow information extraction, we have like more complex and so on. It's vast task. It's not a, of course all of these are quite complex, but at least they refer to a single type of task, whereas information extraction is a huge bandwidth of algorithms. Next, we have language modeling, which builds models for a language. What I mean by that is, of course, I've just used the same words, but what it means is instead of it goes back to our discussion on generative versus discriminative models, where we generate a model for a language. We say that this is how language behaves, and in the next week we will be looking at embeddings, which have this language modeling in them. So we have developed these embeddings which compress words into vectorial form, and they represent aspects of the language. So that is language modeling. And language modeling, of course, existed before deep learning as well. All of these tasks go through the three phases that I spoke about, like symbolic AI and machine learning and deep learning. The interesting thing is, before deep learning, all of these NLP tasks had very different ML models. For example, entity linking would use something called a conditional random seed. Parsing would use Bayesian model. So these are different ML algorithms. What deep learning did is, for all of these tasks, it unified it together and used the same embedding. So that is the power of deep learning. So there is, I think, no NLP paper now that does not use deep learning because of its efficiency, not because the others are bad or something. You can imagine there's a lot of human in the loop for the other models. Next, we have lexical normalization, which is basically changing ungrammatical text to grammatical. There's a lot of research going on tweet analysis, and we do, because we have this 140 character restriction, we are not going to be writing Shakespeare level prose in tweet. But ungrammatical text is a nightmare for NLP algorithms. Grammatical text itself, we discussed for a good 40 minutes what are the problems. And ungrammatical text, and there's a very interesting problem here called code switching, which is basically when you type tweets, you will be using the English letters, but you'll switch between English and Tamil, English and Hindi, and so on. So how will we make algorithms learn that? That is a very interesting task. So lexical normalization, however, it's not related to code switching. It just changes ungrammatical text in one language to grammatical text. Then we have machine translation. Machine translation is the first success of machine learning algorithms over the symbolic ones. I worked on machine translation in 2012, and there we were still using the symbolic methods, and at that time the symbolic methods were performing better than the Google Translate for that pair of languages. We were working on English to Tamil, Tamil to English, like that. Within 2 years, I think the Google score went up like anything, because that is the power of using deep learning and things like that. And the reason we were also successful using symbolic was because we did not have enough data to do machine learning methods. By 2012, machine learning had become the norm for machine translation. But it was quite hard to do it for Indian language. Next is multitask learning. Multitask learning is to basically take a combination of all the tasks I talked about and build a unifying model. Something like in physics, we try this, unified theory, something like that. So a unified theory for NLP, so as to. Next is we have named entity recognition, which is to recognize an organization or a person. You might think that's very straightforward. Um, to give an example, I had a sentence like Ram and Sita went to the market. The NER tagged Ram as person and Sita as an organization. I even looked it up. Was is there some organization called Sita? I could not find, but for some reason the NER was tagging Sita as an organization. It could be because such nouns were not seen in the original dataset on which it is trained. Most of the NLP tasks, we use things that are already trained. So that also gives us a kind of bias because we don't know on what data it was trained. Next is part of speech tagging. So all this constituency passing, dependency passing, all of them depend on part of speech. So part of speech is the base for any of the tasks you have. And we saw like time flies like an arrow, it is not straightforward either. But we have almost, it is considered a solved problem. Next we have question answering. Question answering is the holy grail of NLP tasks because it is the it brings out all the complexities I spoke about. It is both understanding and generation, and it involves a lot of semantics as well. Next is relation prediction, where you have two entities and you say what is the relation between them. In the sense, if I say, if I have a long sentence with Delhi, India repeating, the relation prediction should be able to extract from the text that Delhi is the capital of India. That sort of a thing. This is relation, oh, that is relationship extraction. Relation prediction is you give these two words, Delhi and India. The algorithm will parse through text and find out that it is the capital. Textual similarity is useful for many things like search and so on, where you want to find similar pieces of text. Then you have semantic parsing, which is different from the other parsing we've seen. In the sense here, depending on the domain, we have a meaning for it. So you want, so this is also a huge field like information extraction. What you want to say is that I have complex natural language text and I want to change it to an intermediate, making understandable text. Sort of like the information extraction we saw. In information extraction, we saw, okay, this person is an agent. This is the source. This is the destination. That is the first step of semantic parsing, which is called semantic role labeling. Then the next is how these are related. Who is the agent of what? That connection is in semantic parsing. Sentiment analysis is quite popular. You say whether your reviews are positive, your movie reviews are positive, your actor reviews are positive or negative, politicians are positive, negative. Today, data is immense and this has become very important to, this has become a form of PR analysis almost. Next, we have shallow syntax analysis, which is the first part of the normal constituency parsing and so on. Then we have simplification. In Wikipedia, you might have noticed some of the text is in simple English. There's English and simple English. Some of it is generated using AI, using the simplification algorithm. So summarization. Summarization, you have two types, abstractive and extractive. In extractive summarization, you basically pick out text from sentences from the text and generate the summary. In abstractive, you generate from scratch the sentence. In taxonomy learning, as the name suggests, you're basically learning a hierarchy of things. Like how I was telling, like apple is a fruit and so on. You learn taxonomy, and you can imagine it's quite hard. There's a lot of inheritance involved. Temporal processing is very interesting. You take a piece of text and you order the events in the line of their time. So if I'm reading a story, particularly this is true for historic events or even things that are related in the recent past, what happened first, that kind of an analysis. Text classification is a overall theme, because even sentiment analysis is after all text classification and so on. And we have seen word sense disambiguation in a lot of detail today. So this was my PhD problem. I worked on problems like this. This is what I'm going to quickly summarize. What is the difference between symbolic and machine learning and deep learning, because my thesis was on comparing the three of them. What are the pros and cons of each? So if I have a word problem, John has 5 apples, he gave 2 to Mary. How many does he have now? Now this is question answering, and it has 2 layers of question answering. It's basically, the first layer is the language understanding, and the second layer is to get the mathematical equation for that. So we have co-reference resolution. He gave 2 means he refers to John. And to what? 2 apples, that is also co-reference resolution. Now, knowledge-based approaches, what we would do, we would manually classify the types of word problems, identify the information. Now, this is interpretable because I know what rules have been applied. Do you know precision versus recall? Okay, I'm just going to give a quick overview. Precision basically means out of the correct, out of the ones that I have got as correct, out of the, okay, how do I, maybe I should write this. So basically, if I have 50 positive examples and I classify 40 as positive, so 40 out of 50 is precision. Basically, out of whatever I attempted, how much is correct? But I might not have attempted many. That is the problem of knowledge-based approaches. A lot of relevant things I would not have even attempted because the rules were not applicable. So in spite of the high rule-making effort, I would not be able to generalize. So to give an example, a rule-based NLP approach would be, okay, I manually remove the conjunctions. I split it into simple sentences. I do co-reference resolution. By manually, I mean written rules. I don't mean a human is writing. Basically, the program will see patterns and fill. So then I would get a representation like this. John has 5 apples. Mary has x1. John gave 3. Mary has x1 plus 3. John has 5 minus 3. Now this is very interpretable. It is very useful if you want to teach people. So data-driven approaches, you basically guess the equation. Now this will attempt everything and it is bit precise, but it is not interpretable. But the advantage, as I said before, is that they are comparable. So though there is a high annotation effort, it is less than the rule-making effort. Now deep architecture is a step further. You directly guess what the answer is. It is not at all interpretable, but it is highly generalizable. So to give an example, why this problem is hard. So these are the sort of equations that deep learning struggles with. So Sally has 3 apples, John has 4 apples, Kathy has 5 more than Sally. So how much does Kathy have? 5 more than Sally means 5 plus 3. So how many do they have altogether? It is 3 plus 4 plus 5 plus 3. Now here there's a repetition of the number 3. This is very difficult for a deep learning method to follow because it will try and find out, okay, I have 3 numbers. Should I include all of them or should I, and what is the operator in between? There would not have been an example like this at all to show that you have to repeat the number 3. The next one is a much more complicated example where you involve age concepts and you say Sally is 10 years older than Mary. In 6 years, she will be twice as old. How old are they now? So I know the difference between them is 10 and in 6 years. So it will be like S plus 6. She will be 2 times n plus 6 it will come. If you simplify it, you will basically get back S minus 2n is 6. But if instead of twice as old, it was thrice as old, you will get this equation. S minus 3n is 12. Now the number 12 is not even in the word problem. So what will the poor algorithm do? So how we worked on doing is we kept the non-simplified equations and tried to train the data set. Even then it was quite hard because it is not understanding that age means that, it's going to affect all the variables. So this is the last slide I have, which is the Chinese room experiment. And this is what we suffer in language a lot. So we are developing these algorithms. Imagine I don't know Chinese at all, but I know the rules and the way I am changing. So a person gives a sentence, I look up what it is, and I give the translated sentence. But when I come out, I have no knowledge of what Chinese is. That is where deep learning algorithms are right now. They're very efficient, very good at giving human results, but you cannot question it further. There is no memory, there is no understanding of what language is. That is why question answering is very hard. There's no context, there is no sequencing of events. And that is the challenge we are all working in the research community to bridge. So yeah, thank you. I'm done for the day. And please do write in your doubts if you have anything. And like no doubt is like silly or something like that. One of my favorite doubts has been a student asked me why we measure minima by differentiating and things like that. And I'd love to have such discussions in the last class. So please send in your doubts. Thank you.